Okay, so we're going to prove that if A is any event and C sub 1 and C sub 2 form a partition of S, then the probability of A is equal to the probability of A intersection C sub 1 plus the probability of A intersection C sub 2. All right, so let's first draw a picture to sort of illustrate what's going on here. So here we go. Okay. So this is our sample space. So, and we're going to have an event A here. All right. So when it says that C sub 1 and C sub 2 form a partition of S, that means that the union, so C sub 1 union C sub 2 is equal to S, and their intersections are, their intersection is 0. And C sub 1 intersection C sub 2 equals the empty set, okay? So it'll look something like this. So this is C sub 1, and let's say this is C sub 2. So notice their union is equal to S, and their intersection, they don't share any elements because this line indicates their separation. So that means that they share no elements. So this is what it means to form a partition of S. All right. So at least intuitively, hopefully you can see that the probability of A, so that's all of this. The probability of A is all the blue, right? And we say that that's equal to the probability of A intersection C sub 1. So A intersection C sub 1 would be this purple, right? And then let's get another color. Let's go for red, okay? And the probability of A intersection C sub 2 is the red, right? So notice that the purple plus the red gives us all the blue, right? So the probability of A would be the probability of A intersection C sub 1 plus the probability of A intersection C sub 2. All right, so let's go ahead and prove this. All right, so proof. All right, so the first thing is we know C sub 1 and C sub 2 form a partition of S. So this implies that C sub 1 union C sub 2 is equal to S, and C sub 1 intersection C sub 2 equals the empty set. Well, I know that if C sub 1 intersection C sub 2 is equal to the empty set, then surely, so let me actually write that here. So I'm going to use this piece. So C sub 1 intersection C sub 2 equals the empty set. This implies that A intersection C sub 1, right? Intersection A intersection C sub 2 is equal to the empty set as well, right? Because A intersection this, intersection A intersection that would equal the empty set as well. Okay? Well, this means that A intersection C sub 1 and A intersection C sub 2 are mutually exclusive events, right? And of course, you could see that in the picture, right? A intersection C sub 1 is the purple, and A intersection C sub 2 is the red. And notice that they're mutually exclusive, right? So we know they're mutually exclusive, so we can use our axiom 3, right? So I'm going to have, so I know that A is equal to A intersection C sub 1 union A intersection C sub 2, right? I know that my A is equal to A intersection C sub 1 and A intersection C sub 2. Their union would give me all of A, right? So of course, this implies that the probability of A is equal to the probability of A intersection C sub 1 union A intersection C sub 2. And since these two are mutually exclusive events, by axiom 3, I know that this is equal to the probability of A intersection C sub 1 plus the probability of A intersection C sub 2. So I have that the probability of A is equal to the probability of A intersection C sub 1 plus the probability of A intersection C sub 2, which is exactly what I wanted to prove.